This is the second part of the lecture. I don't know. It's kind of, there's a lot happening. The first part was on Lewis structures only, and then this video is going to be more about how that structure impacts physical properties, and we're going to talk about intermolecular forces. But before I jump into that, I want to go back to this really quick. I mentioned before that in the other video that chemistry just prefers symmetry, and that is true. That's true. But there's more of an explanation, and I felt like I wasn't telling the whole truth. And I have a problem with lying. So it has to do with something called formal charge, which is something we will never ever have to do in this class. But if you do take chemistry classes beyond this one, you will run into formal charge. And that's just a whole long process that I'm not going to show you in this video. I had to come clean about that thing that I said. Anyways, polarity in intermolecular forces is where we're headed for this video. If difference in electronegativity, so pause. What is electronegativity again? That is an atom's ability to attract electrons towards itself, and especially in a bond. So if we have two atoms that are bonded together, we're going to compare their electronegativities, and each atom has an electronegativity associated with it. For example, chlorine has a 3.0. Fluorine has a 4.0. It's the strongest. Hydrogen has a 2.1. And I'm not going to ask that you memorize these. This will always be given to you. But if we take the difference, so we subtract them from each other, and that difference is less than 0.5, we're going to go ahead and say that bond is nonpolar, meaning that those electrons are being shared evenly. If we do a difference in electronegativity and it falls between 0.5 and 1.7, we're going to say that that bond is polar, meaning that those atoms are not sharing their electrons evenly, and one is hogging it. The more electronegative one is hogging electrons. It doesn't really want to share, but it has to. And then the weaker one, or the less electronegative one, has less of those electrons. And what we see happen, like in this chlorine-hydrogen bond, is something we call a partial charge. That's what this lowercase delta minus is. So on the more electronegative side, the one that's hogging electrons, it has a partial negative charge on that side of the molecule. And then on the less electronegative side, where it has less electrons, it's going to have a partial positive charge. So even though overall this molecule is neutral and it's balanced, we see that uneven distribution of electrons, and this is going to play a role in its intermolecular forces. And what are those, you say? Intermolecular forces are attractive forces that make molecules sticky. That's how I think of it. They like to stick together. As you know, opposite charges attract. So if we have a bunch of hydrochloric acid, that's what this is. These partial negative charges are going to be attracted to the partial positive charges of another molecule. And so that's going to make them more sticky. And how we would say that in science terms is it has stronger intermolecular forces. And then there's actual names for those forces. That would be a dipole-dipole force. I'm not going to ask you to know the different names and types, though. And unless, of course, you're so curious because chemistry is your passion and you want to know, then I'll tell you. Just let me know. But if we compare the intermolecular forces and the nonpolar bonds, this one's nonpolar because we have two of the same atom, which means that they are equally strong, so they have to share those electrons evenly. It's like a game of tug of war, no one's winning. We have a perfectly even distributed electron cloud here. And what that does is there's no partial positive, no partial negative side. So there's really nothing that's going to cause this molecule to be attracted to other molecules of the same type. So it's a weaker intermolecular force. There's still a little bit of attraction, and that's just because they're physically in contact with each other, especially if it's a liquid or a solid. So there's a tiny, tiny, tiny bit of attraction just because they're touching. It's kind of like friction, if you will. But that's much weaker than something that has a polar molecule with a partial negative and positive. Okay, so I just said all that. Polar molecules generally have stronger intermolecular forces. It's the moral of the story here. So, how does that influence the physical properties? A molecule that is overall polar is going to have stronger intermolecular forces than nonpolar molecules, like I just said, like 6 times. When comparing nonpolar molecules, though, so let's say we have two nonpolar molecules, types of molecules, and we want to know which one is stronger, we're going to look at the one that has a larger surface area. That one's going to have stronger intermolecular forces. Again, think of it like friction. If you have a longer molecule with more surface area, they have more points of contact for those molecules to, contact each other. So that's going to just have more quote unquote friction. That's what I'm comparing it to. That's a stronger intermolecular force than a shorter molecule that has less points of contact is going to have weaker intermolecular forces. When intermolecular forces are stronger, this is going to increase the substance's boiling point, melting point, and surface tension. Versus when intermolecular forces are stronger, the substance, this is the same thing. If intermolecular forces are stronger, the substance's vapor pressure will decrease. So that one's kind of different. And these are two new physical properties that we're discussing here. So surface tension, what is that? It's a little bit more complex than you would think, which is fine, but I'm going to have a hard time explaining it. That's okay. Surface tension, though, is a measure of intermolecular forces pulling molecules inward from the surface. So because molecules that are like within, I have a picture somewhere. No, I don't. If you have a cup of water, molecules that are in the middle are going to experience more intermolecular forces than ones on the surface because there's nothing above the ones on the surface. Basically, if intermolecular forces are stronger, that whole situation where molecules are being pulled down from the surface will be more, and it's going to take a certain amount of energy to overcome this. And that is surface tension. What that does, though, it's what we see when you see a spider walking across the water. It's what it sounds like. It's almost like the liquid is being pulled tight like a drum, and this little guy is not breaking those forces of attraction between those molecules. So it's able to walk on the water. That's surface tension. That's as far as I'll go. It is more complex than that, but that's as much as you need to know. On the flip side, we have vapor pressure, and that is the pressure exerted by vapor over a liquid in a closed container. So basically, these are supposed to represent two liquids. And what happens is, even if we're not at the boiling point, there are some molecules that will escape being a liquid and will enter the gas phase. If the intermolecular forces are stronger, so these molecules are more attracted to each other, then we'll have less molecules that can escape that liquid phase into the gas phase. And so we have a lower vapor pressure when there's more attractive forces or intermolecular forces. Versus if there's weaker intermolecular forces, more of those particles are going to be able to escape the liquid phase, and therefore we have a higher vapor pressure. Really quick, I just want to show you what I mean. I did not remember to include this in the PowerPoint, but it's worth it to show. I'm going to look up the boiling point. Wow, that's not how you spell words. Boiling point of water versus, yeah, let's go with ethanol. That's comparable to water. Let's see. Wait, no, ethanol has polar. It's polar. So I want something non-polar. Let's say ethane. That's non-polar. You wouldn't need to know this. Why isn't this just simple? Okay. Ethane, blah, 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 has a boiling point of negative 88.5 degrees Celsius or negative 127 degrees Fahrenheit, which is super, super cold. That's when it's going to enter the gas phase because those intermolecular forces are so weak. It wants to be a gas. It doesn't want to be held down. Whereas water, as you know, has a very high boiling point of 100 degrees Celsius, and that's due to those intermolecular forces holding that into the liquid phase. It can't escape. That's a higher boiling point. Same with melting point. Yeah. I don't know. I bet I didn't even have to Google anything to make that point. But yeah, that's it. I'll stop talking now. Good luck out there. Bye.